entered, I guess, into the part of the class where we're starting to talk about numerical methods. So I think I just introduced a little bit at the end of last class the idea of entropic regularization. So we're starting with, I guess abstractly, we're trying to solve this problem. What I wrote like this, the Kantorovich problem. Gigantic linear program. I think I called this L epsilon. And then the idea we thought about a little bit last time was to regularize it a bit. Sorry, this isn't L epsilon, this is L. And instead, try to compute the minimum to this regularized problem. Right, so same objective function, but then with this entropy term on the end. And we suggested a form for this regularizing term, this entropy, to be, okay, we add up over all the components of pi. Pi is this matrix. And then we have something that looks like pi log pi. Okay, and we made a couple observations last time. One is that this regularized problem has a unique minimum. Right now, our new objective function is strictly Comex, so that's nice. And two, the regularizing with this entropic term is going to try to somehow smudge out our transport map. Right? So we're not expecting it to get a really clear transport map anyway. We're going to get this sort of smudged out plan. But hopefully in this smudging, this smearing, we're going to have something that's easier to compute. At the very least, we have now a well-posed problem, which we may or may not have had before, because we may or may not have had uniqueness before. So we need to worry about a couple things. One, what happens as epsilon goes to 0? Are we actually computing the right thing as epsilon goes to 0? And then secondly, if we're happy, if this limits to the right thing, how do we actually compute this in practice? We need an algorithm. So those are the two questions we're going to try to address today. So question one, I guess, is how does the solution of this behave as epsilon goes to 0? Okay, and my claim, this better be the case if this is going to be a useful approach, is a couple things. One, as epsilon goes to 0, the solution we get to this converges to a transport plan that actually minimizes the original problem. That's good, we want that. Now, we know the original problem may or may not have a unique solution. So then the second part of this claim, which is probably not surprising, that it picks, of all the solutions in here, it picks the one that has the highest entropy. And that shouldn't be surprising, because if we're trying to minimize this minus h, obviously, we're going to try to make entropy as high as possible. Okay, so this is the first result that we're going to try to convince ourselves of. Okay, so let's let pi epsilon be the minimizer of this, of this regularized problem. And pi epsilon is uniquely defined. So this is a well-defined object. Then my claim is that as epsilon goes to 0, this thing is going to converge to a transport plan. And like I said, it's going to be the one that maximizes entropy. Okay, so we'll write this as, now again, we're restricting to feasible transport plans. of the feasible transport plans, we want to maximize entropy subject to the condition that not only is this a feasible plan, it's actually a minimizing plan for this guy. So subject to the condition that now C pi, our objective function, actually gives us the minimal value. Okay, so that's true. And also, the minimal value of this should converge to the actual minimal value of this, right? And if it does that, then this would be a proxy for the Wasserstein metric. Okay, so this is true, and this is true. Okay, so let's see if we can try to argue that this is really the case. Okay, so I'm going to start with a sequence of epsilons going to 0, and try to see if we can get some convergence in this sequence. So let's choose some epsilons that go to 0. Obviously, we want positive epsilons. Okay, now we've used the fact before that this constraint set, right, this is a set of probability measures, and if we're working on bounded domains, this is a compact set, right? So since this is compact, we get a sequence of pi epsilons. We can always extract a convergent subsequence from that. All right, so there's going to exist a subsequence, say n sub k, such that pi epsilon n sub k is going to converge to some pi star. Yes, this is true for compact sets. And pi star is still feasible. Okay, so now I want to try to take this pi star and hopefully prove that it's an optimal for the original problem. So I'm going to take something that's optimal for this problem, and I'm going to compare it to pi star and see what happens. Okay, so let's choose any optimal pi, so any pi that's both feasible and optimal for the original problem. So by that, I mean that our objective function is equal to the minimum. Okay, this guy may or may not be uniquely determined, but there is certainly a minimizer. Okay, and now let's try to use what we know about how these things are defined. We have optimality conditions, right? Pi epsilon is the minimizer of this, and pi is the minimizer of this. So we can write down conditions for that, right? If I plug pi in here, I'm going to get a bigger value than if I plug pi epsilon in here. And the reverse is going to be true up here. So by optimality, I should get that okay, if I look at my original objective function, right, pi epsilon is going to give me a bigger value than pi. Okay, so I can use that, and then again I'm going to use what I have here, that C dotted with pi epsilon is going to be less than or equal to C pi minus H pi plus H of pi epsilon, right? Just rearranging this condition a little bit. So we also have that this guy here is going to be less than C pi minus epsilon H of pi plus epsilon, this is epsilon n sub k, of pi epsilon. And then this is still here. All right, so I've just fed in the two optimality conditions. Okay, which if I simplify, this looks like a difference of my two entropy functions. Okay, so let's try to make a couple observations here. One is that the entropy of pi epsilon is going to be bigger than or equal to the entropy of pi, right? And that was one of the things that we wanted to show, is that pi epsilon tries to maximize entropy. So if I compare it to any optimal map, it should have a bigger entropy. So certainly we have that this is the case. Now, secondly, what do I want to do? I want to take epsilon to 0. I'm hoping that when I take epsilon to 0, this goes to 0. And all of a sudden, I have the difference between my two objective functions going to 0, right? In other words, the objective function applied to this, applied to pi star in the limit, minus the objective function, which is optimal, is 0. So then we've actually got something optimal. So what do you think? What happens as epsilon goes to 0? Does this whole term go to 0? Now, this is just some number, right? The issue is what happens to this as epsilon goes to 0. Is it bounded? Exactly. So what do you think? Is it bounded? So we actually answered this question last class. We said, okay, forget about optimal transport. Let's just look at feasible plans. How do we maximize entropy, right? And we found a maximizer. We can actually maximize entropy. So we also know that H of pi epsilon nk, whatever it is, it's going to be less than or equal to H of mu nu transpose, this outer product between our source and target densities, this transport plan that says everything gets to go everywhere. And this is again, this is just some number, some finite value. Okay, so this is bounded. Okay, so I say, great, this is bounded, this is bounded. So as I take epsilon to 0, this goes to 0. I have a 0 on the other side, so taking epsilon to 0, we get 0 equals the limit as we progress along our sequence. Okay, and if pi epsilon is converging to pi star, then this product, right, this linear relationship will also converge. So this limit is indeed C pi star minus C pi. Okay, so this is the optimal value. C pi star is also equal to the optimal value. So pi star, the limit of this sequence or this subsequence, actually recovers the optimal value. Okay, so C pi star is indeed this optimal value. Okay, and pi star, of all optimal values, pi star is the one that maximizes entropy, right? It has higher entropy than any other optimal plan. Okay, so pi star is optimal for the original problem. Okay, and it maximizes entropy. Okay, so it maximizes entropy among all other optimal plans. So we're almost done. We started with a sequence, which gives us a sequence of pi epsilons. We extracted a convergent subsequence, right? And the key is I could have started with any sequence here, right? So what do I have? Give me any sequence you like. I can extract a subsequence that converges to pi star, all right? That's the condition that says, actually, my original sequence also converges to pi star. Okay, so since for all choices of epsilon n, there exists a subsequence such that pi epsilon nk converges to pi star, right? Always the same pi star. Then indeed pi epsilon converges to pi star. Okay, and then as an immediate consequence of that, we're going to get that this value converges to the optimal value, right? Because C pi epsilon converges to C pi star, which is optimal. This is bounded, so this term is going to converge to 0 as epsilon goes to 0. So we also right away obtain that the values converge. Questions? You happy with that? Okay, so this is at least a reasonable thing to try to compute, right? We're not going to just get junk out of this if we compute with small epsilon. We're going to get something that's close to the plan that we want, close to the value of the Wasserstein metric that we want. From here to here?
Yes.
Okay, yeah. Okay, so what did I use here? I used that C pi epsilon minus epsilon h of pi epsilon is less than or equal to C pi minus epsilon h of pi. Right, pi epsilon is defined as the minimizer of this object. Okay? So with that, all I did was move this epsilon h pi epsilon to the other side.
You just rearranged it.
I just rearranged it.
Thank you.
Yep. Any other questions? Okay, so we're computing this smeared out plan, right? this is just, we've sort of talked about this already. If we have something like this, maybe this is my F, and this is my G shifted. Okay, then if I try to look at my pi, the real pi is going to be sparse. So it's going to, along this combination of x and y, it's going to be non-zero. And everywhere else, it's going to be 0, right? It's going to say this value of x wants to shift up to this value, and this value wants to shift up to this value, and so on. But everything else, no mass is moving between those two values. So this pi itself, pi star, is sparse. In other words, it's 0 off this sort of diagonal, which doesn't have to be a straight line, certainly, for other planes. Pi epsilon is going to take this, going to give us another feasible plan, but it's going to increase the entropy of it a little bit. So it's going to take this and say, here's where we really want mass to be concentrated, but this line is going to be a little bit fuzzy. So pi epsilon would be something like this. Smear out the plan. All right, so again, I mean, we talked about this. You don't really get a transport map out of this. You could try to estimate the transport map. Whether it's accurate enough to actually do anything with is another question, and it may not be. But you get this computation of L epsilon, which approximates L, your Wasserstein metric. And what's nice is for a lot of these applications where you're using the Wasserstein metric, it's not even really important that you have an accurate approximation a lot of the time. So what we're doing there, a lot of the time when we're doing something with Wasserstein metric, what we're really just trying to do is minimize it, right? So all we're interested in is, can I find this value of the minimizer in the geophysics problem or in these machine learning problems? So if I'm minimizing this, or I'm minimizing something like this that's spread out, I don't really care that the values of the Wasserstein metric have big errors in them over here, as long as the minimum hasn't really moved too far. So even for a relatively large value of epsilon, you might actually be perfectly fine with this in some of these applications, because you're just trying to get the minimizer or something close to the minimizer, depending on the application. So low accuracy is not necessarily a bad thing here. You'll accept low accuracy if you have an algorithm that can handle very large-scale data in a lot of these problems. So this is really, I guess, the goal in an algorithm here. We want an algorithm that handles large-scale data. And something always has to give. We would be willing to sacrifice accuracy. Again, that's not always true. It depends on your application, but for a lot of these, that's the case. If you're trying to do something with optics, for example, you probably want accurate transport maps and accurate computation of view. But the nice thing is those are not such large-scale problems. They're actually kind of genuinely two-dimensional problems. So you can put a little bit of work into getting more accurate solutions. So this is the goal. Can we find, for positive epsilon, can we find a really efficient method for doing this? Subject to the fact that we may have a very large, pi is big. It lives on the product space, and it's hard to even write the whole thing down all at once sometimes. So we need an algorithm that somehow can represent pi in a very efficient way. So this turns out to be a key observation, which It's probably not going to be obvious when I first write it down, but it ends up being the key that really makes this work. We can interpret pi epsilon as some kind of projection. So what pi epsilon does is it starts with a really, really simple coupling between our source and our target, a really simple coupling that you can just write down straight away, just depending on the cost function, without any work. It takes this and it projects it. It projects it down onto couplings that actually satisfy the constraints, that actually conserve mass the way they're supposed to. So this is, and we'll see where this comes from. We can interpret pi epsilon as I said, the projection onto our constraint set of a very simple coupling. So then what do we have to do? We have to be able to write down this coupling, which is easy. We're going to write it down. And then the hard part is then we have to find a way to somehow project this onto our constraint set and define what we mean by projection. So here's the coupling we're going to start with. We're going to start with this Gibbs distribution, okay, that we're going to apply to our cost matrix. Okay, so this is again going to be an n by m matrix, similar to pi. It's not going to have the right marginals or anything like that. It's just going to be some sort of rule that says mass, maybe a lot of mass wants to move from here to here, or maybe the values are low and mass doesn't really want to move from here to here. So this is the coupling. And it's the exponential of minus Cij divided by epsilon. Okay, so what happens? If C is very large, so the cost of moving from I to j is very large, then this exponential takes on a very small value, right? In other words, if the cost of moving from I to j is very large, we don't really want to move, this doesn't really want to move mass from I to j. Only a very small proportion of mass is going to try to move. If the cost of moving from I to j is very small, say it's close to 0, then this value is large, and then this coupling is saying, yeah, we're actually happy to move a lot of mass between these 2 points. So it's just sort of the simplest, crudest almost way that you could ever try to couple these things is just to say, if the cost is low, let's move more mass, and if the cost is high, let's move less mass. This is big, like this is as big as pi is, but you know, we don't have to do a lot of work to store this thing, right? We just have to be able to compute the cost matrix, and then we can compute this if we need it. Okay, so how do we use this? Well, we need a way now to take this and say, great, it's kind of intuitively does something that's maybe natural, but obviously doesn't satisfy our constraint set, and it's probably not optimal. It's not even feasible. So we need to do some work to at least make this feasible, because we need a feasible plan at the end of the day. So we need to somehow project this onto our constraint set. And we need to define the projection in a way that makes sense and that's actually going to give us our pi epsilon at the end of the day. Like, you know, with a projection, we're typically saying, let's try to minimize the distance between this and this set, but you can define distances in lots of different ways. So we need a distance that is kind of natural to our problem. And one of the things that's really important in this problem, in this regularization, is this entropy term. So what we're going to use as some sort of distance is what's called the relative entropy between distributions or between plans like this. And it's going to have very much the same structure as this entropy here. Okay, so we want to minimize, and we'll show that this gives us the result we want. Okay, we'll call the relative entropy. Okay, between this Gibbs distribution and our actual constraint set. So here's one way of measuring whether two distributions are close to each other or not close to each other. And again, it's a way that mimics the structure of this thing. This is the Kkt Leibler divergence. Okay, between these two plans, pi, which later is going to be something that's feasible that lives in our constraint set, and k is this Gibbs distribution. Okay, is okay, so we'll write it like this. So the sum over all these components of pi log pi over k minus pi plus k. All right, this certainly has some structure in common with our entropy that we used before that we're using to regularize. Right, we've got our kind of pi log pi minus pi that showed up before. It's sort of funny as a distance, if you will. It's not actually symmetric, right? So the divergence between pi and k is not the same as the divergence between k and pi. But what it does do, which is important, is it's minimized if pi is equal to k. I can make that argument for you. So it is asymmetric, which is kind of weird. But it is minimized when pi equals k. And that's certainly something that we want if we're talking about trying to find the plan in here that's as close as possible to k. You know, if we happen to find something that's exactly equal to k, then it should pick this. Minimizing this divergence or distance should pick that.
Is the non-symmetry related to the entropy of the universe?
The non-symmetry, yeah, the non-symmetry is related to the entropy. We'll actually see, when we do the calculation, we'll see how the asymmetry actually gives us exactly, it makes things in one line simplify to exactly what we want. So you can almost, work backwards from this is the entropy we know we have. How do we have to define this thing in order to make this simplification happen? Of course, that's how most proofs work in practice. I'll give it to you in the nice flowing direction, but it was done in reverse, trying to reverse engineer what this thing had to look like. I know you said you want me to start teaching like that with all the dead ends and wrong ideas.
I've heard other people have the same similar idea.
Yeah? Okay, so I'm just going to do kind of little quick exercise on this. So let's just restrict to one component. So if I restrict this thing to just one component, effectively I can think of this as, okay, a function of two variables. So pi log pi over k, I'll write it out like this. Okay, minus pi plus k. Okay, and my claim is this is a minimum when pi and k are equal to each other. Okay, so let's just, there's nothing fancy about this. I'm just going to start computing some partial derivatives. So f sub pi is, okay, so pi and 1 over pi is 1 plus log pi minus log k minus 1. We don't need those. F sub k is minus pi over k plus 1. Okay, setting, so if we're looking for a minimizer, setting the gradient equal to 0, indeed gives us that pi is equal to k. Okay, and if we want to know if this is actually a minimizer and not, say, a maximizer, which would be problematic for what we're trying to do, then we need some second derivatives. So let's say f pi pi is 1 over pi. F k k is pi over k squared. And the mixed derivative, okay, this with respect to pi is minus 1 over k. Okay, so we know that if we're trying to characterize minimizers, we need to look at the Hessian of this thing. Okay, so the Hessian is going to be equal to, I have 1 over pi, off diagonal I have minus 1 over k, minus 1 over k, pi over k squared. Okay, and ideally, we'd like this to be positive definite. Okay, it's a 2 by 2 matrix. Do you know this trick for checking the eigenvalues are positive of a 2 by 2 matrix? If you check that the trace is positive and that the determinant is positive, then the eigenvalues are all positive. So the trace of this thing is 1 over pi plus pi over k squared. This is positive, right? Because these plans are always greater than 0, greater than or equal to 0. So certainly this is positive. Okay, so the sum of the eigenvalues is positive. The product of the eigenvalues is going to be 1 over k squared minus 1 over k squared, which is 0. So this matrix it's not positive definite, it's positive semi-definite. We've got one vanishing eigenvalue, and it's globally positive semi-definite, right? I didn't use the fact anywhere that pi was equal to k. Globally, this is positive semi-definite. Okay, for all values of pi and k. There's no concavity changes trying to happen in here, right? when I find a place where the gradient is 0, that's my minimizer. Okay, so f is minimized when pi is equal to k. I guess this condition means we should expect this kind of degeneracy because we expect that sort of along this line where pi is equal to k, f is actually constant. So if it's constant, then its second derivatives in that direction are also 0. So we should probably expect a 0 eigenvalue here. Okay, so with two variables, this thing is minimized when pi is equal to k, and the minimal value is 0. And that means, component-wise, each term that shows up in this sum is minimized when this component of pi is equal to this component of k, right? So if each term in the sum has a minimum when those components are equal, then the overall sum is also going to be minimized when pi is equal to k. So indeed, this divergence is minimum when pi equals k. Okay, so this now is my claim. I said it before, and I'm going to write it down with the correct mathematical details, is that pi epsilon we get by taking this Gibbs distribution and projecting it down onto my constraint set. And by projecting, I mean trying to minimize this KL divergence. So I claim that pi epsilon is indeed the argmin over all feasible transport plans of this divergence. Right? We take our Gibbs distribution, which was just a super simple coupling that kind of did reasonable things, and we find the feasible plan that's as close as possible to it, where as close as possible is defined in this sense, using this KL divergence. Okay, so let's try to prove it. Okay, so first of all, we know that pi epsilon is feasible. Okay, the definition of pi epsilon requires it to be feasible. Okay, so what do I want to do? I want to say, let me take any other feasible plan pi and say that if I put any other feasible plan in here, I get a larger value of this KL divergence, right? In other words, pi epsilon is the one that wants to minimize this. That's our goal. That's where we're trying to go. And having the goal in mind is important when you're trying to reverse engineer the type of distance you want to use, for example. So we have a goal, and we can write down the things that we know. So what are the things that we know? It's the same things that we kind of wrote down last time. We know where pi epsilon comes from. It comes from a minimization problem. So actually, let me write one more line here. Let pi be any feasible plan. We need to compare them. Okay, and we know that if we look at the objective function on pi, this will be bigger than if we look at this objective function on pi epsilon. Pi epsilon was defined as the minimizer of this thing. And I'm going to divide out an epsilon here, which you don't have to do. You can do it at a later step if you want to. It doesn't matter. Okay, so let me write out exactly what this entropy is. We expect when we write out exactly what this entropy is, we are hopefully going to get something come popping out that looks a lot like this KL divergence. Okay, so if I write out exactly what all of this is, what do I have? So here I have this sort of dot product between C and pi. So here I have a Cij pi ij divided by epsilon. Okay, here I have minus of the entropy. So this is going to give me a pi ij log pi ij minus 1. And then same game for these terms here. So Cij pi epsilon ij over epsilon minus pi epsilon ij log of pi epsilon minus 1. Okay, multiplying out by this 1 here, I think I mentioned before, it's not that important that the minus 1 is here because when we add up all the pi's, we're going to get 1. And then we add up all of these pi epsilons, and we're going to get 1 because they're both feasible. Those we're not so worried about. Here we have a log term. If we could write this as a log term, we could combine all the log terms together. So we can always do that by a little bit of manipulation. And then as I do this, you're going to see the things we wrote down pop out. And if I hadn't written them down before, you would still be able to look at it and say, I wonder if that's something interesting to look at, something useful to look at. Okay, so let's try to rearrange this a little bit. So I have pi times a log term. So I'd like to write this as pi times a log term. Okay, so what am I going to do? I'm going to write it as minus pi times the log of the exponential of minus Cij over epsilon. Right, this looks familiar. This is our Gibbs distribution, right? So it's not that somebody had to guess ahead of time. Let's just try the Gibbs and see what happens, right? It pops out here. At this stage, I haven't used anything about KL divergences or Gibbs or anything like that. I just wrote down what I knew. Okay, so I have that minus pi. I have plus pi log pi minus pi ij. Okay, and then I do everything again for pi epsilon. I had all of this minus same deal with pi epsilons. Okay, so if we try to simplify this a little bit, combine my log terms a little bit, I have pi log pi over this exponential. Okay, minus pi ij. And then the same thing with the pi epsilons. So minus pi epsilon ij log pi epsilon plus pi epsilon ij. Are we missing some ij's, possibly? Any other ij's that you would like me to add? So this should start to look familiar, right? This is the Gibbs distribution, which again, it just popped out on its own without me forcing it. And this overall looks like a KL divergence, I think modulo of a plus Kij that I'd need here, which I could then minus Kij here, no big deal. Okay, the KL divergence looks super mysterious the first time I wrote it down. Why does that have anything to do with this problem? But it fell out right here without me having to do anything about it, right? If I was just going to manipulate this problem, I'd say, let's start writing down what I know. Let's try to simplify it a little bit and then say, I would guess that this is an interesting quantity. Okay, I look at it a little bit. It doesn't quite have the minimum at the right place, or it doesn't quite have the minimum when pi is equal to k, or a minimum of 0. But with a plus k here, that shifts it where I want it to go, right, with minimal manipulation. So this is indeed the KL divergence between pi and k minus the KL divergence between pi epsilon and k. Okay, and this, if we go back to where we started, this is greater than or equal to 0. That's the key takeaway. So if I were to kind of summarize that in one line, what do I have? I have that the KL divergence between pi epsilon and k is less than or equal to the KL divergence between pi and k for all feasible pi's. Okay, and that's what we wanted to prove, right? We wanted to prove that we could interpret pi epsilon as this projection, this minimizing this divergence among feasible plans. So this is exactly where we were trying to get. Any other questions on that before I move on?
Wasn't the claim that pi epsilon is equal to the argmin of KL?
Yeah, that's exactly what I've got here, right? So no matter what other plan I compare it to, pi epsilon gives me a smaller value of KL. So that means that pi epsilon is the minimizer.
So that relates back to the original linear function that was L, or no?
So KL is this KL divergence, right? But yeah, so pi epsilon, we know that as we've proved already, as epsilon goes to 0, pi epsilon converges to pi star,
Oh, so we're using
this optimal plan. Yeah. So we already know that pi epsilon is a thing we'd like to compute. We're just trying to learn more about pi epsilon. And this is sort of another way of interpreting pi epsilon. Yes, it's a regularized version of our optimal transport problem, but also we can think of it as this projection. Yeah. is it easy to minimize KL? So that's the obvious question. Okay, great, we have this other interpretation, but how do we compute this thing? This is still a big object. How many unknowns are living in this thing? N times n, yeah. So right now, if we want to be able to characterize pi, we have to solve for n times m unknowns, which may be enormous. You think of n being, the number of unknowns or the number of discretization points you have in a typical problem in 2D or 3D. Okay, that's already too much to deal with a lot of the time, right? It's already expensive. But now we've taken that and we've effectively squared it and said, actually, this is how many unknowns we have. And now we're going to be building matrices that are completely intractable to work with. And this is a big problem. So yeah, how can we find an efficient way to solve this? Or another way to say it, how can we find a way of characterizing this that involves way fewer unknowns, and hopefully unknowns that are easy to compute? So let's go back to the original optimization problem. Okay, so our optimization problem was this. We want to minimize, this cost function, which we've regularized with the entropy, subject to, we have some equality constraints and some inequality constraints. So pi 1m is equal to mu. Pi transpose times one vector is equal to nu. And all of these pi's are positive. All right, so let's try to characterize this a little bit. What's one way you know of characterizing the solution of a Comex optimization problem? I know some of you took optimization. What are some conditions we have that tell us if we're at a minimum? The Kkt conditions, yeah. I don't want to have to report back to Professor Shirkoff that nobody's remembered anything from that class. So you have saved your colleagues here. Okay, so let's think about the Kkt conditions. Let me write something abstract here. So say we're trying to minimize f subject to g is less than or equal to 0 and h is equal to 0. Okay, then the Kkt condition should look like this, that we're going to relate the gradient of f to, so some term that's going to multiply our inequality constraint. And some term that's going to multiply our equality constraint. Okay, and we expect a couple other conditions. Okay, so now we just need to plug our problem into this framework and see what else we can learn. Okay, so our problem, we need the gradient of this with respect to pi. Pi is our unknown, right? So here, the ij component of the gradient is just going to be Cij. And then we need the gradient of this entropy, which we've computed before. It's just this log term. Okay, so if I do it for my problem, I have minus Cij minus epsilon log pi ij. Okay, I take the gradient of my inequality constraints, right? I'm going to get a lot of 1s. Okay, so if I look at the ijth component, I'm just going to get a minus 1. Okay, and then my equality constraints are in 2 pieces here. So I'm going to get 1 for each value of I. And again, I've got just a lot of 1s popping up here. And then I'm going to get 1 of these for each value of j. So if we're interested in particular in the ijth component, I'm going to find the relevant value of I, the relevant value of j. Okay, so I'm going to get a plus lambda I plus sigma j. Okay, and then kappa ij should be greater than or equal to 0. Kappa ij times my g was my inequality constraint, so times pi ij should equal 0. And if we can find a solution to this, the solution is the minimizer, because we had a nice convex problem that we started with. Okay, so I'm going to play the game that I did before. Let's just try kappa equal to 0, right? If it works, again, if we find a solution, then that's great. That's the solution. So we can try kappa equal to 0. Okay, and then what do I have? If I put that in here, I have log pi ij equals, so minus Cij over epsilon, minus lambda I over epsilon, minus sigma j over epsilon. Okay, and I'm trying to solve for this optimal plan. So if I try to solve for this, what do I get? The exponential of minus Cij over epsilon, that looks familiar. It just keeps popping up on its own. I'm not forcing it. It just keeps coming. Something that depends on I times something that depends on j. Which, okay, in a more compact form, this is my Gibbs distribution. This is something that depends only on I, and this is an unknown that depends only on j. So what does this mean? This means if I could find these u and v, I would fully characterize pi, right? If I could find u, and u is a vector with n components, and if I could find v, which is a vector with m components, then I would know pi. Then you said to me, I want to know pi at this location. I'd say, okay, great. This, easy to calculate. One line in your calculator. This I know, I multiply them together. So this is a characterization of the optimal plan, but it's a characterization that involves much fewer unknowns, right? Now we only have n plus m unknowns instead of n times m. Okay, so this characterizes the optimal plan, the optimal regularized plan using only n plus m unknowns. Okay, and what determines U and V? Mu and nu, exactly, my equality constraints. I still have to satisfy these equality constraints. So indeed, Ui and Vj are going to be determined by my equality constraints, by expecting pi to have the right marginals, in other words. All right, so let's try to figure out what this gives us. Okay, so first of all, I'm going to write pi this way. Pi is a matrix. It's a matrix whose components are written this way. So I can write this in terms of matrix multiplication. If I take the elements of U and I just create a diagonal matrix out of them, the same with the elements of V. Okay, so this is going to be diagonal of U. That's an n by n matrix times K, which is n by m, times the diagonal of V. Okay, and what do we require? Well, we require that if we multiply this by a one vector, we get mu. Okay, so this we can simplify a little bit. So we take diagonal of V and multiply it by a one vector, right? And we're just picking out a particular component of V at each line. So this we can really think of as K times V. So another way to write this would be, I guess, how am I going to write this? Diagonal of U times KV is equal to mu. Okay, this is a vector, this is a vector. We're just dotting these vectors together, basically. We're doing component-wise multiplication. So another way to say this is U. Here I mean component-wise multiplication, KV is equal to mu. Okay, this means component-wise multiplication. Okay, so for each constraint, I need one element of this vector, right? And it'll give me the one element of U. Okay, and similarly, my other constraint is going to turn into Ku dot multiply V. I guess K transpose U is equal to nu. Okay, so we're trying to compute this entropically regularized transport plan, which was a massive problem to start with. Now we've reduced it to this. So computing, or fully characterizing pi epsilon has been reduced to, okay, the problem of finding these vectors u and v. Okay, such that these conditions are satisfied. So u dot multiply kv is equal to mu, and v dot multiply k transpose u is equal to nu. So we need an algorithm for doing this. So if I just gave you those and said solve them, what's the first thing that you would try? Newton's method, okay. Newton's method is always a good option. We could try something even simpler and dumber than Newton's method. Newton's method has the disadvantage that you have to compute this Jacobian, which if we're lazy and we're trying to do something really fast and easy. Okay, so let's say I give you some initial guess, and you're always going to start with some initial guess, and I say now try to update u and make it better. Okay, you're thinking gradient descent. I'm thinking even simpler and dumber. So the simplest, dumbest thing I could think of, because you never do something complicated unless you've tried the simple, dumb things first. So the absolute easiest sort of fixed point type iteration I could think of is, and this makes sense because we've got this sort of component-wise multiplication. This isn't real this is not like we're trying to invert a matrix here, but you know, these are almost scalar problems that we're trying to solve. Is we start with initialization, and then we say I want to update u. Well, I know component-wise u multiplied with kv is equal to mu. The ith component of this times the ith component of this equals the ith component of this. So let's just try to solve component-wise for the ith component of u. All right. So I'm going to write this as component-wise division with kv at my last guess. Right, that's like the simplest, dumbest thing I could do. I don't have to know how to do anything. I don't have to know how to invert matrices. I just have to know how to do scalar division. And then I also have to update v. So component-wise, I'm going to do this. So I need to know how to do division of scalars, and I guess I need to know how to do matrix multiplication, matrix vector multiplication. All right, so this simplest, dumbest thing that you could try to do, which also has the advantage of being, this would be very easy to code, right? It'd be very easy to parallelize, right? Because I mean, I'm basically doing this one component at a time, so I don't need to know what's going on with the other components in order to do these. Similar with this matrix vector multiplication in here, right? I don't need the whole result of this multiplication. I just need one component of it. So those could certainly be spread out over different processors. So this is very parallelizable, and this is known as Sinkhorn algorithm, which is becoming extremely popular in especially the machine learning community. Because when you're working with huge things, simple and dumb and easy to code, right, has an advantage. Sophisticated tools are great when that's what you need, but if you don't need them, why use them? So this is Sinkhorn's algorithm. which I like. If I wanted to, I could put this on a homework assignment and say, code this up for me next week, and you could do it, no problem, right? It's like 2 lines of code, 3 lines of code. So let me just list a few pros and cons of this approach. So some advantages of, okay, we've way reduced the number of unknowns, right? From n times m to m plus m, which is very good. So the number of unknowns is like wildly reduced. Okay, from this big number to this much more tractable number. It's very easy to parallelize, which is very good if you're trying to work with large-scale data. Okay, the hardest thing you have to do in here is this matrix vector product. When that's the hardest thing that you have to do, you're kind of laughing. So we have to do matrix vector products that involves this Gibbs distribution. Okay, and depending on the structure of your problem, there may be tricks for actually accelerating this. Because again, this isn't just any old matrix, it's a matrix with a lot of structure. So sometimes there's tricks for doing this or doing this approximately very efficiently, better than you could do just straight up matrix vector multiplication. You can do some convergence analysis. So these are a few of the good things I could think of. And they're very good. There's a reason this is a popular algorithm. One of the big reasons being that you can write it in 2 lines of code. And people, people who are non-experts in a field and they're looking for a method, they don't want to code up all sorts of complicated things that stretch on for thousands and thousands and thousands of lines. They want something that they can write in 2 lines of code. There are some downsides. Okay, we said we don't get a transport map. At least we don't get a very good transport map out of this, right? Because this transport plan gets all smudged. So this is a great method, but it's not for every application, certainly. As you take epsilon smaller, the convergence deteriorates. That's probably not surprising that that typically happens with regularized problems. You run into, as you start to take epsilon small, you run into stability issues often. So when I say deteriorate, it can very seriously deteriorate as epsilon goes to 0. So certainly, bad things happen when epsilon is too small. Okay, and sort of a consequence of that is we're restricted to relatively large epsilon and consequently low accuracy. Now, again, for some applications, you might be perfectly happy with low accuracy, right? A lot of these times we're trying to compute the Wasserstein metric. We have a huge amount of data. We just need to get an approximation quickly. If it's a little off, it's fine. It's no big deal. So again, it's problem dependent. It's application dependent on whether this is going to be a deal breaker for you or not. So that is entropic regularization and Sinkhorn's algorithm. Any questions on that? Yeah.
How would you know to even write down the KL projection?
So to write down the KL projection, so in real life, I wouldn't have written it down at the beginning of that proof.
Right.
I would have written it down at the end of the proof. I would have started by saying, I want to compute pi epsilon. We kind of decided that already. And then I would have started the proof as I started it without having the KL divergence there. I would have just said, pi epsilon minimizes this problem. So let me write down what that means. And okay, let me plug in what the entropy is and start simplifying. And as we simplify, it's gone now. As I simplified along the way, at some point, we said, here's something that looks like the Gibbs distribution, right? We had these e to the minus c over epsilon terms, which I didn't force in them. They just came out when I simplified. And then we had this sort of structure, the things that looked like pi log pi minus pi came out. So you might very easily say, there's structure here. I wonder if I tried to define a distance by exactly what is sitting here in front of me, right? And then you look at it, say, it doesn't quite have a minimum where pi equals k, but maybe if I just like shift it, add a k to the end of it, okay, that shifted it to where I need it to be.
So the k projection naturally pops
It
up.
really naturally pops up. Yeah, no, you would never start by saying, at least I wouldn't. Some people do. Some people have different approaches. Some people start their proofs and they just start writing the proof, and then they get to the end and it's done. I don't do that. I iterate. So my first lines of a proof are, this is what I want to show, and I work in reverse, but it's sloppy, and instead of having a proofs, I just have pictures usually in the first version of a proof. This is what I want, and this is a picture of what I think might happen, and here it looks like the slope might be getting too big. I wonder if that's true, and that's version 1 of a proof. And then you start going through and say, can I make this more rigorous? And you see what pops out. And in this case, this thing that looks like the KL divergence pops out. And if it's me, at least, I would not have written that on the first iteration, certainly. Any other questions?
There will be a better method.
So there's no one-size-fits-all numerical method. So what I would say is the method that you want for any problem depends on what you're trying to do with your method, what you want it to accomplish. So if I want to get a rough approximation to the Wasserstein metric quickly on large-scale data, then this is a great method. If I'm trying to compute the surface of a lens, this is not the method that I want to use, and you want to do something else. So that's why as we go forward through numerical methods, I'm going to kind of split things up into semi-discrete problems, discrete problems, continuous problems. Everything we do for now, we'll try to come up with an actual map. But the methods you want are going to depend on what kind of problem you have and what kind of application you have in mind, and things like that.